Continuing with my earlier part, let me take up something which is totally new. Most of you think ceramics are insulators. They are used in light poles where they prevent short circuiting of the current carrying wire to the earth. Most of it think as paper cups, refractories. All of you have got refrigerators with self-closing doors which have a magnet. Today, that magnetic material is a ceramic material which is based on barium hexaferrite. This is a magnetic ceramic which has got a very high remanescence, means the magnetic strength stays for a very high long time. The common Alnico magnets, which are made of aluminum, nickel, cobalt, they rust, magnetic field decays, but in barium hexaferrite the magnetic field does not decay. The advent of magnetic ceramics, you can see, has changed your refrigerator door. You now have clips which you can fix on walls so that things hang from it. What is there? It's a polymeric suction cup loaded with barium hexaferrite. It's a magnetic material. Those are available off the shelf in any bookshop. But the most significant change you will see is for those of you who are lucky to live in cities, especially cities where the police force has been more organized, is the handheld mics they use, as opposed to common microphones in rather many places where they have got large mics with power supplies. The police use handheld mics which weigh hardly 1 kilogram and has got very high throughput power. This has been again possible through use of ceramic magnets. Cell phones. I am still using this Nokia second generation cell phone, while most of you would be using today much more touchscreen ones or the Android version phones, whatever. What is at the heart of this cell phone? Where does ceramic come here? You have got this battery. This is a lithium ion battery. This one, if I take this one and the latest battery in iPhone, which of course I do not have, there is a sea change, because iPhone has a lot of apps running. It requires very, very high current density and longevity. And from these lithium battery phones, which came into, this is a 1995 product, today the capacity has increased lots of times. In this cell phone, the small mic which is over here, there is a earpiece, the mic is back here. Again, this has been possible due to magnetic ceramics. If you happen to look at the iPhone 4, which has just come into the market, you will see that it does not require a scratch proof pad. Most of you use a scratch proof pad, like in this mobile, this top one is a plastic which is scratch proof. But in the iPhone 4, you do not require it. Why? Very simple reason. The iPhone 4 is coated with a very thin glass ceramic, which I talked of earlier. Now, here is the interesting point. I cannot take the iPhone and dip it into molten glass. Obviously, this glass has to be deposited on the iPhone at temperatures which is much lower than 110 degree. So, when I talked of this glass ceramic being fabricated at temperatures melted at 1350, heat treated at 550 to get this glass ceramic, this cannot be applied to iPhones, because I cannot immerse the iPhone in molten glass. We will come to it to show you how ceramic coatings can be deposited at very low temperatures, which has today made iPhone possible. It is simply coated with glass. Another difference, a place where ceramics comes to play, is in the standard phones, landline phones, you have wires and blah 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 which convey the message, whatever it is. Your TV needs a cable to have the images transmitted. How can we talk in this? Where is the aerial? None. What it has, even this cell phone has, is a microwave resonator. This microwave resonator picks up the microwaves and concentrates so that the processing circuit in the cell phone can get the signal correctly. This is again made up of ceramics. You see, ceramics today pervades, as you will see going on, a lot of our lives. Another area where people who are living in cold regions, where car windows tend to get, if the car is lying outside, it will be covered with snow. And you can clean off the car window when you start it, but what happens when you are driving? In most of the cases, if this is the, let us say, the car window, the front window, what is done is these are transparent indium tin oxide coatings. Again a ceramic. So here I am now using a ceramic which was formerly thought of only as an insulator, also as a conductor. So these cars which drive, which are used in snowbound areas, they have a thin coating of transparent indium oxide. You switch the, flick the switch on, these get heated and the snow falls off the car, or the snow cannot get deposited in the car. There are examples which will abound at home where you use whatever you use. Your today's modern kitchen chimney, which are the higher end ones, not the lower end ones, lower priced ones. The kitchen chimney has a very vital safety attachment. In kitchen you use LPG gas. This is heavier than air. And hence, in case of gas leak, this settles to the floor. You cannot smell it. It is below your nose level, yet LPG is leaking. So today's kitchen chimney, which suck the air out from the area around the gas ovens, they have incorporated LPG sensor. A sensor which can measure liquid petroleum gas. The first such sensors which looked like this were made from zirconium dioxide containing yttrium oxide. Now, why this I will come to later, but the main part is zirconium dioxide. Fundamentally, I will take another example and then come to it. Fundamentally, zirconium dioxide, this when heated can lose oxygen, which goes off, leaving a vacancy here. If I draw this diagram, let us say this is metal, this is oxygen, metal, oxygen, oxygen, metal. On heating, it loses this oxygen, let us say, this oxygen goes out on heating. So what happens is this one oxygen has gone out, it has now become charged. So the valency of zirconia will drop. This also happens in case of copper oxide, zinc oxide, iron oxide, and a host of other transition elements. Because of this, they become conductors. Now, zirconia is basically an oxygen ion conductor. So, if we had the earlier zirconia sensors, there has been a huge advances then, but this is how the first zirconia sensor was used, is this sensor was put in exhaust gas. What will exhaust gases have? They will have unburnt hydrocarbons, they will have carbon monoxide, NOx, all of this. This part was flushed with air. Zirconium oxide became being an O2 minus ion conductor. If the outside of this was coated with platinum and so was the inside coated with platinum. Now, a potential was applied right across this. So, what happened is this, that the hydrocarbons got oxidized over here. They reacted with oxygen to give you CO2 plus H2O. CO reacted with oxygen to give you CO2. NOx reacted with give you oxygen to give you NO2. Now, all of these reactions are electrochemical reactions. So, here what we have is basically an electrochemical cell at this surface. O2 comes in, they react with the carbon dioxide, carbon monoxide, they react with the hydrocarbons, they react with the NOx. So, a potential is generated. Now, instead of supplying a potential, we measure it here. What we will know is the amount, is the potential generated, which is proportional to the oxidation of these gases. So, this sort of a sensor is used today. Of course, now the form has changed. It's a film form. Today, what we have is a basic substrate on which we have a thin film of zirconia maybe or other sensors and a heater at the bottom. If I am looking from the top view, I will have a van der Pol connection. This is the volts and this measures the current. Because each of these reactions, burning of the hydrocarbons, carbon monoxide, nitrous oxide, requires different potentials. In the automobile, wherever you go for your automobile exhaust checking, what it does, it scans across the potentials, finds out how much current is flowing and tells you how much of the hydrocarbons, carbon monoxide or the NOx are there. In the kitchen chimney, which I talked of, a similar sensor is incorporated, and that helps in reduction of gas explosions in kitchens. And today it is a routine thing to be had in any major kitchen of any hotel. In a car, about today the Volkswagen Passa, whose advertisements you see in the papers, which can park itself. By the time you will be seeing this lecture, that advertisement will become very common. You don't have to touch anything, it parks itself. How? It has sensors in the front, in the sides, it determines where it is. Volkswagen Passa uses around 20 kilograms of ceramics in it. The ceramics are there as washers on the doors, so the doors move very smoothly. The ceramics are there as sensors for the multi-point fuel injection machine, for sensing proximity, for sensing if the driver is falling asleep, is just loaded with ceramics, very tiny small elements, but things which make travel safer. Even the fact that when you are driving you have not put your seat belt on is sensed by another ceramic sensor. The car will not start unless you put your seat belt on. Inside the engine, the piston rings which are used in any automobile today, starting from Maruti, they have got ceramic piston rings. But the most important one that I will show you is at the heart of the engine, which is the spark plug. This spark plug, this is the heart of any engine. What does it have? It has the white part is aluminosilicate ceramic. It is coupled to a metal which can be threaded, which is threaded and is screwed on top of the engine. What happens is this spark plug is connected to a oscillating supply which is 10 kV and it fires 4,000 times a minute. What happens? This part is grounded. The 10,000 kV signal comes in through this and the spark is generated between this gap. Yeah, the gap is showing, and that burns the fuel. The beauty of this system is it is totally gas tight. It is absolutely gas tight, even though it has two dissimilar things. The ceramic, which has got a very low thermal expansion coefficient, and the metal, it will have its thermal expansion coefficient. Here you are seeing only the external part. There is this seal between the ceramic and the metal is gas tight. But what you forget over here is there has to be another one. If I look at the internal construction, this is the white ceramic part that you see. Through it comes the metal part. The metal part at the top, this is the metal which comes through. This has to be gas tight. Then there is carbon powder, and finally the projecting piece of the metal. This is the outer part which has threads and all of that. So what we are dealing with over here is gas sealing at two different areas. Over here, that is the external knurled knob and the ceramic, and also over here the internal one which goes inside. You have to appreciate that the voltage applied here is cyclic. It is 10 kV at 4,000 times per second. So obviously, when the spark flies between here and here, this spark will be flying at that frequency. This is fixed inside the engine hub. This is where the piston ring is. This is where the piston ring is, which goes up and down. So every time it fires, once in 4,000 times per second, there is a huge mechanical shock also generated. For those of you who have been unlucky to touch the spark plug just after it has been stopped, your fingers will burn. The temperature will be as hot as 300 degrees centigrade. This is further subjected to mechanical shock. And yet, this is the plug that does not fail you, yet this is a plug that withholds its integrity and it works. If the plug has ever failed you, it's because you have not cleaned the plug. And you know the production rate of this plug at any industry? 1,000 pieces per minute. This is so fast. So you see, ceramics, automobiles, jet engines, they are all interwoven together. And they play a huge role in making travel safer. The next one is something that affects everyone. We often break our bones, orthopedic joints, and often the fracture is so compound that the doctor does not have a choice other than to use titanium plates. He will put the bone back, he will use titanium wire, titanium plates, titanium screws to screw the plates together. However, this has problems, because let us look at the fact that this is a bone which is broken, and what the doc is doing, he is merely taking two plates, pressing them here and then tightening by screws. Now, titanium is biocompatible. True. Body does not reject it. But the problem with using plain titanium is that screws and plates come loose. Why is the reason? The simple reason is, when in your body, if these are your body, these are your muscles, here is a broken bone, and the doc has put in the titanium plates over here. Muscles do not grow in. That is, it is as if you are immersing your hand in water and taking it out. So, one of the biggest problem of using pure titanium plate, which is biocompatible, is that it does not become a part of the body. Today's titanium plates, which are used, or screws, they have a coating of porous hydroxyapatite. This hydroxyapatite is a real bone material. True, we make it, we synthesize it, but this is porous. And because it is porous and it is very well adherent to the titanium plate, muscles can grow in. And the titanium plate does not come loose from the muscles. Today, if you are looking at any implant, if it is a metallic implant, it will have a hydroxyapatite coating, which is a ceramic. These titanium plates are warranted to last in your body for 10 years, but they do fail, because with time the titanium gets corroded. So, if this titanium plate gets corroded, the strength comes down and well, fracture can recur, especially if it is for a geriatric person, because his bone will never heal here. It will not have the full strength. So if this titanium plate corrodes, he is in trouble. So today, if one is looking at, say, implants, say knee, hip, anyone, the other type of implant other than the metallic one available is a ceramic implant. Where the hip joint or the knee joint is all ceramic. It's perfectly biocompatible and it's warranted for life. This is expensive, but it's warranted for life because bone growth, muscle growth occurs straight away and it's not rejected like plain titanium plates were. In dental restoration, for those who suffer from defects of the teeth, today alumina based dental implants are available off the rack. In major places, all they do is they drill a hole in your gum, screw the dental implant in, and nobody knows it's a ceramic implant. The most important change is where it is coming is in the field called tissue engineering. A vastly expanding field where total reconstruction can be possible. So far, if you lost a bone, if you broke your leg, and it was broken so bad that it could not be saved, your prosthesis. But suppose my hands, my fingers are gone, prosthesis is also there. However, if my face is blown away, these jaw lines, these are blown away, which is a real thing. You have to understand that there's a total number of people killed in small localized wars, say in Korea War, war in Cambodia, Vietnam. There is one phase. The other phase is Kosovo, Kuwait, Afghanistan, Iraq, Mideast wars. The number of people killed in each of those areas is much more than the total number of people killed in Second World War. Because it's a low intensity conflict, it is dependent on regional thing, nobody pays attention. But there's one thing that is happening in common over there and for which attention has to be paid, is in most of those cases, due to the explosions of mines, more often claymore mines. Claymore mines are mines which are banned, yet they are in widespread use, which jumps 5 foot above the ground and then explodes and blows your jaw bones, your cranial cavity, everything away. What do you do in that case? You don't have a prosthesis for that. It is where tissue engineering is coming into play in a huge way. I won't dwell on this today here. I'll take it up when the time comes. Uh, Tissue engineering is now changing a lot of things. We can re-engineering the human body. Defense is a major area where ceramics play a huge role. Be it for brakes, be it for the runways, be it for the sensors, um, in structural components, ceramics plays a huge role. For example, in missiles, let's say if you ever if you Google up cruise missiles, or any other missiles which are launched from afar, they have to enter the airspace and then hit their target. Let us presume a missile shape which is like this. A missile shape like this, which is a nose cone. Because it will suffer atmospheric re-entry and friction, this nose cone will get heated. Furthermore, this nose cone houses the tracking sensors. I won't dwell on what the tracking sensors are. For example, for cruise missiles, it does land terrain tracking. You can look these up in Google, on the net. Terrain tracking. It follows how the terrain looks like, which has been pre-programmed into its computer memory. There are satellites which emit microwaves or radio waves which go out, are reflected back, and then it is then used for homing in. The only material which satisfies all these requirements are again ceramics. This part, which is the top part, this is called the radome. You can Google the word radome, you can Google the word cruise missiles or any other missile, and you can find out enough information on the net because you are intelligent enough, and see what it is. It's true, you will not find how it's constructed, but at least you will know its function. How it is constructed is for me to tell you somewhere down the line in this course. I have talked of insulators, resistors, capacitors, ferroelectric components, microelectronics, sensors a lot. I would only point out to one particular type. If you have been perceptive enough or you have been looking far, you have seen the high tension lines, 33 kV, 132 kV and more. Those towers have brown colored insulators, whereas the ones which take current power to our home are white colored. Why are those high tension insulators brown colored while the ones which are on the lamp posts white colored? The simple reason is this, that the ones which are brown colored are long, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, they carry the electrical line which carries 33 kV or 132 kV or whatever, depending on the power supply. It can go up to 400 kV. This particular insulator will over time collect dust. Now you know that as in this spark plug, when a sufficiently high potential is there, it generates a spark. Due to the presence of these dirt materials, there are local sparks which are generated, and this is called corona discharge. If this corona discharge is not controlled, due to the sparking there will be local melting, and as a result this insulator will be destroyed, leading to total power outage. So the brown coating which is there on top of the insulator does serve a purpose. Those high tension insulators are all coated brown. What is that brown coating? This brown coating, what does it do? If there is a spark, it conducts the current so that sparking does not occur. It is highly resistive, has a low can conduct current, and it is based on Fe2O3. It is an iron oxide based coating, which by normal means is highly resistive, but if such corona discharges occur, as I have said over here, under the action of the corona discharge, it provides an alternate pathway so that arcing or sparking, if you prefer the word, does not occur at these points and avoid catastrophic failure of these high tension insulators. Now this high tension insulator and the low tension insulator which you see by the roadways, they are made of the same material, same porcelain, but this one has a brown glaze. This brown glaze prevents the corona discharge and hence prevents failure of the insulator due to local melting. It is again a ceramic. Fiber optics is something that you see everywhere. They are used for fast communication, is the backbone of communication in India today. I have already talked of TV, radio and microphones earlier. The last item I will talk of is a very important one, tribological coatings, corrosion resistant materials. This particular spectacle I am wearing, this is made up of fiberglass, rather polymer fibers. It is about 4 times less heavy than it would be if it was made of glass. This is not only made up of polymer fiber, it is scratch resistant. And also anti-glare. Further, this also has darkens in sun. When the light intensity is high, it darkens to cut down. However, let me not dwell on this part, but let me dwell on these two. The very fact that this spectacle lens is a polymer, it can be easily scratched. To prevent it, again a ceramic coating has been applied so that it does not scratch. Further, this is anti-glare, so that if you are facing an intense beam of light, it cuts the glare down. This is one type of tribological coating I talk of. One type of tribological coating. Another type of tribological coating I would talk of would be modern jet engine blades. Due to intellectual property restrictions, I cannot show the figures. However, I would strongly urge you to look at the images through Google as to how jet engine blades are, because they are the mode of travel. By the year's end or early next year, you can travel from Delhi to London within an hour and a half, a journey that takes close to 12 hours now. Have your meeting, fly down to Denver, Chicago, anywhere in another hour's time, hold your meeting, fly across the Pacific to say Tokyo in 2 hours' time, and be back at Delhi by 10 p.m. All this fast mode of travel, which today would have taken 3 or 4 days, something that will happen late this year if everything goes right, or next year, is simply because of advances in turbine technology. Turbines means the jet engine turbines, turbine technology. In the existing aircrafts of the air forces around the world, ceramic coatings, that is, I would rather mention what coating, zirconia stabilized by yttrium oxide or calcium oxide coatings are applied on jet engine blades. Why? Because the jet engine sucks in huge amount of air, dust particles also come in, and they erode the jet engine blades, leading to failure. To prevent it, most of the advanced jet fighters have their blades coated with this zirconium oxide ceramic. The coating technology which I talked of on top of the polymer fibers in this lens is entirely different from the way these jet engines will be coated. The two are coatings by name, but the technology differs totally. And in the transport, whatever I was talking of, when I can fly out of Delhi, hold my meetings in England, USA, Japan, and fly back by 10 p.m., they will be using ceramic turbines. It will no longer be metallic. And what will that allow? That will allow higher compression ratios, better fuel burning efficiency. And this is another extreme of a tribological material, tribological coating. So, between my spectacle lens and the jet engine, there is a huge range of applications where ceramics are used for scratch resistant, wear resistant applications. For those of you who are photographers, the biggest demand on the camera is it won't cause optical aberration of the image, because an SLR camera has as many as 36 lens elements, and when light refracts through each, there can be optical aberration, there can be light dispersion. So, each of those lenses are coated rather, with proprietary ceramic coatings, so that light aberration, light dispersion does not distort the image that you take. Here, for those who are professional photographers, they know very well that some cameras made in certain country, in a particular country, it never grows fungus, because fungus is the biggest enemy of coated lenses. But all other lenses made in other countries grow fungus. So, even the design of the coating has to be such that it is corrosion resistant. I will end this lecture with something that affects all of us. It is, I am about to be affected, I am at that old age. Most of us won't escape it. Cataract in the eye. Lot of us who as our seniors going for cataract operation frequently ask the doc, can I have a cheaper lens? That is the biggest foolish thing that one can do, because if you buy a 10 rupee glass from which you drink water, as opposed to a 100 rupee glass, and if you hold both of them up before your eyes, you will see that the 10 rupee glass has got a lot of bubbles in it. It is a very defective glass. I brought up the subject of cataracts because in most cases we have our priorities wrongly placed, even when it is about vision. So, if I ever have to have a cataract operation, I will go in for the best glass and not compromise there. While I am talking of my eyesight, today's ceramics are used under high performance operation. The space shuttle was lost during re-entry because a soft foam hit the ceramic tile, nobody knew, making a 1-foot gouge, and that blew the space shuttle apart. So, today we are talking of materials that cannot fail, high performance materials on which humans' lives depend on. And hence, in this particular course, we will have to talk of materials that can withstand anything. So, here in this fabrication and processing course, we will start off next day with what the course covers, and then take things from there. For example, I will just end the course with one thing. This is the standard cartridge you use for inkjet printers. This is where the ink has come out from. Wait. Let me hold the angle. Yeah. This is where the ink comes out from. Have any one of you ever thought how do this inkjet printer print say A, which is written differently from B? How does it print Z? What really happens is this printhead is a glass ceramic in which holes have been machined, holes which open and close depending on the potential they get from here. These are the electrical contacts which controls which hole will open and close, and depending on that you have either the letter A or the letter Z. None of you ever thought in an inkjet printer you would have a glass ceramic which is machinable, which is again piezoelectric. I end this lecture here because with this statement, and one more thing, if you look at it, lots of electronic circuits are being printed by this inkjet printer. I leave it to you to Google it and find out for yourself. If you Google inkjet printing, electronic circuits, you will see how this printer head is being used for printing electronic circuits.